Up to this point, you've learned how to take the derivatives of various types of functions, including polynomials, products, natural logs, and more. But how would we go about taking the derivative of something like this, where one function is nested inside of another? In this video, I'm going to show you how to quickly and easily apply the chain rule for problems such as these. Before we get started, let's briefly review composition of functions. Composition of functions can be described as nesting one function inside another, and is usually denoted with a little o between the two functions. For example, if f of x equals x cubed and g of x equals 8x minus 2, then we would say that f composed with g is equal to f of g of x, which is equal to 8x minus 2 cubed. To compose one function with another, it is helpful to write them in nested form like this. From here, we can write that g is 8x minus 2, and plug that in everywhere we see an x in f of x. Similarly, we could write g composed with f as g of f of x, which is equal to g of x cubed, which would then equal 8x cubed minus 2. The chain rule is a method which helps us take the derivative of nested functions like f of g of x. It states that the derivative of a composite function f of g is equal to the derivative of the outer function with the inner function untouched, multiplied by the derivative of the inner function. Another way of expressing the chain rule is by writing it like this. So if we wanted to find the derivative of f of g of x is equal to 8x minus 2 cubed, we would first write the derivative of the outer function, the cube, while leaving the inner function alone. So this outer function is f of x, so f of x is equal to what we'll call x cubed. So the derivative of f prime of x, is equal to 3x squared. So the first part of our derivative will be 3 times x, which is g of x in this case, so 8x minus 2 squared. And this is the derivative, so we'll write our prime sign. Then we're going to multiply this by the derivative of the inner function, 8x minus 2, which is just 8. So we're going to multiply all of this by 8. Then we can simplify to get 24 times 8x minus 2 squared. Now, we could have handled this derivative by FOILing out 8x minus 2 cubed and then applying the power rule to the resulting polynomial. This expansion would have been time-consuming to calculate, though. Once you get the hang of the chain rule, you'll find that it is an excellent time saver in problems like these. Let's work through another example. Use the chain rule to find the derivative of the function h of x is equal to the square root of the natural log of x. First, let's identify what the outer function and inner function each are. Since the natural log of x is nested inside the radical, it is the inner function, while the outer function is the square root. The chain rule says that the derivative of a composite function is equal to the derivative of the outer function with the inner function untouched times the derivative of the inner function. So since the derivative of the square root of x, or x to the 1/2 power, is 1/2 x to the negative 1/2 power, we can write the first part of the derivative like this. So we'll have h prime of x is equal to 1/2 times the natural log of x, remember the inner function is untouched, to the negative 1/2 power. Then we'll multiply by the derivative of the inside. Since the derivative of the natural log of x is 1 over x, we simply multiply by 1 over x. We can simplify a little bit, and then we'll get 1 over 2x times the square root of the natural log of x. Let's do another example. Use the chain rule to find the derivative of the function j of x is equal to e to the 8x squared. Even though this function looks a little bit fearsome, we have the tools necessary to work through its derivative. In this case, the outer function is the exponential function, e raised to a power. The inner function is that power, 8x squared. To get the derivative with the chain rule, we need to first write the derivative of the outer function with the inner function untouched. Since the derivative of the outer function, e to the x, is itself, we're just going to write e to the 8x squared again. So j prime of x is equal to e to the 8x squared times, then we need to multiply this by the derivative of the inner function. Since the derivative of 8x squared is 16x, we can multiply by 16x. Then we can rewrite this just a little bit to get 16x e to the 8x squared. Not so bad, right? Now I want you to try a problem on your own. Using the chain rule, find the derivative of k of x is equal to x cubed minus 9 to the 11th power. Remember, you'll need to handle the outer function's derivative first, then the inner function's derivative. Pause the video now to work out the answer yourself. Then we'll discuss the solution together. Did you get it? Let's check your work now. What is the outer function? In this problem, it is the 11th power. The inner function is x cubed minus 9. The first part of the chain rule dictates that we write the derivative of the outer function with the inner function still inside of it. So we'll have k prime of x is equal to 11 times x cubed minus 9 to the 10th power. Then we're going to multiply this by the derivative of the inner function. So the derivative of x cubed minus 9 is 3x squared. If we simplify this a little bit, we'll get 11 times 3 is 33, so 33 x squared times x cubed minus 9 to the 10th power. This problem, like the first one in this video, could have been solved by expanding the polynomial to a 12-term expression and then handling each term individually with the power rule. But I think it's safe to say that the chain rule is a much better method for finding this derivative. Let's work through one last example. Leo is studying population growth in a petri dish of mold spores. The dish starts out with only one spore, but the spore duplicates itself, and there is exponential population growth over time. If the number of mold spores on day x can be calculated using the function m of x is equal to e to the square root of x, determine the function m prime of x, which represents the growth rate on day x. Because we are interested in finding a rate function, m prime of x, we understand that this is a derivative problem. And since the function m of x is a composite function, we know that we are going to need the chain rule to find that derivative. The outer function in this case is the exponential function, e raised to a power. That power, the square root of x, is the inner function. To find m prime, we start by taking the derivative of the outer function while leaving the inner function as is. Once again, the derivative of e to the x is itself, so we'll start by just writing e to the square root of x again. So we'll have m prime of x is equal to e to the square root of x times. Next, we have to multiply this by the derivative of the inner function. Since the derivative of the square root of x is 1/2 x to the negative 1/2 power, the growth rate for the function m prime is then equal to e to the square root of x times 1/2 x to the negative 1/2 power. Or we could rewrite this as e to the square root of x over 2 times the square root of x. Remember, the chain rule helps us take the derivatives of composite or nested functions. To get these derivatives, first write the derivative of the outer function with the inner function still untouched within it, then multiply this by the derivative of the inner function. This technique will come in handy anytime you see a function contained in another function, whether under a radical, in a logarithm, or even inside a trig function. As always, a little practice goes a long way, so I encourage you to try some problems on your own now. Thanks for watching, and happy studying!